Picture this. Right now, as you're listening to these words, there's a cosmic monster lurking just 1,560 light-years away from Earth. It's invisible. It weighs 10 times more than our Sun, and it's slowly drawing in matter from its stellar companion. This isn't science fiction. This is Gaia BH1, the closest known black hole to our planet, discovered just 2 years ago. But here's what might keep you awake at night. Astronomers now suspect there could be hundreds of millions of these invisible giants scattered throughout our galaxy, and the closest one to Earth might be hiding just 40 to 80 light-years away. That's practically next door in cosmic terms. Welcome back to this quiet corner of the universe, where we explore the deepest mysteries of space and time. I'm here to guide you through one of the most fascinating and slightly unsettling questions in modern astronomy. Just how close are we to these cosmic enigmas that bend space and time itself? Tonight, we'll journey together through the dark neighborhoods of our galaxy, uncovering recent discoveries that have completely transformed our understanding of what reshaped our understanding of the hidden structures around us. Before we drift deeper into this celestial mystery, I'd love to know where you're joining me from tonight. Are you tucked into bed in Tokyo, watching the stars through your window in Sao Paulo, or perhaps taking a contemplative walk under the night sky in Stockholm? There's something beautifully connecting about knowing that no matter where you are on our pale blue dot, we're all floating together in this vast cosmic ocean, possibly much closer to black holes than we ever imagined. As always, if you find these explorations soothing or thought-provoking, a gentle tap of the like button helps this channel reach other curious minds like yours. And if you haven't already, consider subscribing for more journeys into the profound mysteries that surround us. Now, settle in, take a deep breath, and let's begin our careful approach to these invisible giants that may be closer than we think. Until very recently, the question of nearby black holes felt almost academic. Sure, we knew about the supermassive black hole at the center of our galaxy, Sagittarius A star, sitting safely 26,000 light-years away. We understood that stellar mass black holes existed throughout the Milky Way, but they seemed comfortably distant, like dangerous animals in a far-off wilderness that felt comfortably distant from our daily lives. Then came 2022, and everything changed. The discovery of Gaia BH1 wasn't announced with fanfare or dramatic press releases. Instead, it emerged quietly from the meticulous work of astronomers analysing data from the European Space Agency's Gaia telescope, combined with ground-based observations from the Gemini Observatory. What they found was both remarkable and scientifically fascinating. A black hole system hiding in plain sight, relatively speaking, in the constellation of Physicist. Gaia BH1 is what astronomers call a stellar mass black hole, formed when a massive star collapsed at the end of its life. With a mass roughly 10 times that of our Sun, it exists in what's called a binary system, locked in a gravitational dance with a companion star remarkably similar to our own Sun. This companion star orbits the black hole at approximately the same distance that Earth orbits the Sun, creating an intriguing parallel to our own solar system, except with a cosmic monster at the center instead of our life-giving star. The discovery method itself reveals the subtle artistry of modern astronomy. The black hole, being black, emits no light that we can see. Instead, astronomers detected it through the gravitational influence it exerts on its stellar companion. The Gaia telescope, with its extraordinary precision, observed tiny wobbles in the companion star's motion, wobbles so subtle they required measurements accurate to within millionths of degrees. It's like detecting the presence of an invisible dancer by watching their partner's movements in a cosmic ballet performed across impossible distances. But Gaia BH1 was just the beginning. In 2024, astronomers announced the discovery of Gaia BH3, located 1,926 light-years away in the constellation Aquila. This black hole is even more remarkable. weighing in at 32.7 times the mass of our Sun, making it the heaviest known stellar mass black hole in our galaxy. What makes Gaia BH1 particularly intriguing is its companion star, which is composed primarily of hydrogen and helium with very few heavier elements. This discovery challenges our understanding of how massive black holes can form from what astronomers call metal-poor stars, providing a window into the early universe when such stars were more common. As you listen to these discoveries unfold, take a moment to consider the implications. These aren't just academic curiosities. Each new detection suggests that our cosmic neighborhood is far more populated with these invisible giants than we previously imagined. The progressive nature of these discoveries, each one closer and more detailed than the last, hints at a universe where black holes are not rare cosmic accidents, but common features of the galactic landscape. The third member of this nearby black hole family is Gaia BH1, discovered in 2023 in the constellation Centaurus, sitting 3,800 light-years from Earth. Together, these three discoveries paint a picture of our local galactic region that's both fascinating and, if we're being honest, slightly unsettling. They represent a fundamental shift in our understanding of how common these enigmatic objects really are. Now, before we let our imaginations run wild with scenarios of cosmic doom, let's pause and consider what these distances actually mean in practical terms. When we say Gaia BH1 is 1,560 light-years away, we're talking about a distance so vast that even our fastest spacecraft would take millions of years to reach it. To put this in perspective, consider NASA's Parker Solar Probe, launched in 2018 to study our Sun. This remarkable spacecraft holds the record as the fastest human-made object, traveling at speeds of up to 430,000 miles per hour. That's fast enough to travel from Edinburgh to Sydney in about 90 seconds. Yet even at this incredible velocity, the journey to our nearest known black hole would take approximately 2.5 million years. The mathematics of these distances reveals both the protective vastness of space and the humbling scale of our cosmic isolation. Light itself, travelling at 186,400 miles per second, takes 1,560 years to make the journey from Gaia BH1 to Earth. When we observe this system through our telescopes, we're seeing it as it existed during the height of the Byzantine Empire, when the Hagia Sophia was being constructed and the Dark Ages were beginning to lift in Europe. But here's where the story takes an interesting turn. The discovery of these three nearby black holes has led astronomers to a startling conclusion. If we can detect three stellar mass black holes within roughly 4,000 light-years of Earth, statistical models suggest there are likely hundreds of millions of them scattered throughout our galaxy. This isn't speculation, it's extrapolation based on detection rates and the observable volume of space. Even more intriguing is the implication that the closest black hole to Earth is probably much nearer than Gaia BH1. Current estimates suggest that the nearest black hole might be lurking just 40 to 80 light-years away, perhaps in a system where the companion star is too faint for us to detect the telltale gravitational wobbles, or perhaps existing as an isolated object with no companion at all. Take a breath here and let this idea settle in your mind. Somewhere in our relatively immediate cosmic neighborhood, there may be a region of space where matter disappears forever, where time slows to a crawl, where the very fabric of reality is twisted beyond recognition. It's closer to us than many of the bright stars we see in our night sky. The event horizon of a black hole, with 10 solar masses, like Gaia BH1, would have a radius of only about 30 kilometers. That's smaller than most major cities, yet it represents a boundary beyond which nothing, not even light, can escape. The contrast between the cosmic significance of these objects and their relatively small physical size is one of the most striking aspects of black hole physics. This brings us to perhaps the most important question. Should we be concerned about these nearby cosmic giants? The answer requires us to understand exactly how black holes behave and what it would actually take for one to pose a threat to Earth. Contrary to popular science fiction portrayals, black holes are not cosmic archives indiscriminately sucking up everything in their vicinity. This is one of the most persistent misconceptions about these objects, and it stems from a fundamental misunderstanding of how gravity works. At large distances, a black hole behaves gravitationally exactly like any other object of the same mass. If our Sun were somehow magically replaced by a black hole of identical mass, all the planets would continue in their current orbits. We would freeze to death from the lack of sunlight, but we wouldn't be pulled into the black hole. The danger zone around a black hole is actually quite small relative to astronomical distances. Earth would only be in real danger if it came within about 10 miles of a black hole's event horizon. Consider that in the context of our current distance from the Sun, 93 million miles, and you begin to appreciate just how close an encounter would need to be to pose a direct threat. However, the scenario changes dramatically when we consider what astronomers call tidal disruption events. If a black hole were to pass through our solar system at a distance comparable to Jupiter's orbit from the Sun, roughly 500 million miles, the gravitational effects would be dramatic for Earth's orbit. The differential gravitational pull stronger on the side of Earth facing the black hole and weaker on the far side could literally tear our planet apart long before we came anywhere near the event horizon. Astronomical models indicate such encounters are extraordinarily rare, roughly a 0.01% probability over the solar system's lifetime. That's a probability of about 1 in 10,000, which sounds reassuring until you realize that with 400 billion stars in our galaxy, this type of dramatic encounter has probably happened to several million planets throughout cosmic history. The timescales involved in potential black hole encounters provide some comfort, even if astronomers detected a rogue black hole heading toward our solar system from a distance of 10 light-years, moving at a typical velocity of 1,500 kilometers per second. It would take approximately 2,000 years to reach us. This would provide ample time for detection and, theoretically, for our civilization to develop some form of response, though the technology for deflecting or avoiding such an object remains firmly in the realm of science fiction. As you contemplate these scenarios, notice how they illustrate a fundamental aspect of our cosmic existence. We live in a universe where dramatic events are statistically inevitable over long enough timescales, yet so rare on human timescales that they remain largely theoretical concerns. It's a reminder of both our cosmic vulnerability and the protective vastness of space and time. The mathematical precision required to detect these nearby black holes also reveals something profound about our current moment in cosmic history. We are living at exactly the right time, with exactly the right technology to begin mapping our local black hole population. A century ago, we didn't even know black holes existed. A century from now, we may have catalogued every black hole within 1,000 light-years of Earth. The story of nearby black holes extends beyond the confirmed discoveries of Gaia BH1, BH2, and BH3. These detections represent only the tip of a cosmic iceberg, the most easily observable members of what is likely a vast population of invisible neighbours sharing our galactic neighbourhood. Consider the detection bias inherent in our current methods. We can only identify black holes that happen to have stellar companions bright enough for us to observe and measure their gravitational dance. This means we're missing isolated black holes, those cosmic hermits that wander through space without companions to betray their presence. We're also missing systems where the companion star is too faint or too distant to show detectable wobbles in their motion. Current estimates suggest that for every black hole we can detect through these indirect methods, there may be dozens or hundreds that remain invisible to our instruments. This hidden population of stellar mass black holes scattered throughout our region of the galaxy, like invisible lighthouses, with their beacons forever extinguished, represents one of the most significant unknowns in our cosmic neighborhood. The implications extend beyond simple curiosity. These invisible neighbors influence the gravitational environment of our local stellar region in ways we're only beginning to understand. Every star, every planet, every comet in our vicinity moves through a gravitational landscape shaped by the combined influence of visible stars and invisible black holes. We're all dancing to a cosmic rhythm, with some of the dancers hidden from view. Recent theoretical work suggests that primordial black holes, formed in the early universe rather than from stellar collapse, might also populate our cosmic neighborhood. These objects could have any mass, from microscopic to stellar scales, and might be even more common than their stellar mass cousins. Some researchers propose that primordial black holes could account for some or all of the mysterious dark matter that makes up roughly 27% of the universe. If primordial black holes exist in significant numbers, the closest one to Earth might be much nearer than even the most optimistic estimates for stellar mass black holes. Theoretical calculations suggest that microscopic primordial black holes might pass through our solar system regularly, perhaps once per decade, creating tiny gravitational disturbances that we might be able to detect with sufficiently sensitive instruments. The possibility of asteroid mass primordial black holes presents a particularly intriguing scenario. These objects, containing the mass of a typical asteroid compressed into a region smaller than an atom, could theoretically pass directly through Earth with minimal disruption. The passage would create a microscopic tunnel through our planet, heating and melting rock in a narrow cylinder, perhaps 10 centimeters in radius, leaving behind a geological signature that might persist for millions of years. As you listen, imagine the profound loneliness and mystery of these cosmic wanderers. Some may have been traveling through space for billions of years, since shortly after the Big Bang itself, carrying within their event horizons the compressed remains of matter from the early universe. Others are younger, the collapsed cores of massive stars that lived and died while complex life was evolving on Earth. While we've focused on the stellar mass black holes in our cosmic neighborhood, we cannot ignore the supermassive giant that anchors our entire galactic community. Sagittarius A star, the black hole at the center of our galaxy, sits approximately 26,000 light-years away in the direction of the constellation Sagittarius. With a mass equivalent to 4.3 million suns, it represents a completely different category of cosmic monster. Unlike the nearby stellar mass black holes we've discussed, Sagittarius A star is not a potential threat, but rather the gravitational anchor that holds our entire galaxy together. Our solar system, along with hundreds of billions of other stars, orbits this supermassive black hole in a grand celestial dance that takes approximately 225 million years to complete. We've completed this galactic orbit only about 20 times since Earth formed, meaning that the last time we were at this same position in our galactic orbit, dinosaurs ruled the Earth. The recent observations of stars orbiting extremely close to Sagittarius A star have provided some of the most dramatic confirmations of Einstein's general relativity under extreme conditions. One particular star, designated S2, follows an elliptical orbit that brings it within just 120 astronomical units of the black hole at its closest approach. That's roughly 3 times the distance from the Sun to Pluto, which sounds like a comfortable margin until you realize that the star is moving at over 5,000 kilometers per second at its closest approach. Roughly, observations earned Reinhard Genzel and 2% of the speed of light. David Andrea Ghez, the 2020 Nobel Prize in Physics, for providing definitive proof that Sagittarius A star is indeed a supermassive black hole. The precision required to track these stars' motions and measure the relativistic effects of their extreme velocities represents one of the greatest achievements of modern astronomy. The existence of Sagittarius A star also provides a comforting perspective on our nearby stellar mass black holes. While objects like Gaia BH1 might seem frighteningly close at 1,560 light-years, they pale in comparison to the supermassive giant that we've been orbiting safely for billions of years. If we can coexist peacefully with a black hole containing 4.3 million solar masses, the presence of 10 solar mass objects in our cosmic neighborhood seems almost quaint by comparison. Take a moment to appreciate this cosmic irony. We've spent this entire discussion worried about black holes that might be hiding 40 to 80 light-years away, while we're actually trapped in orbit around a black hole millions of times more massive. Yet this orbital relationship is not a prison, but a cosmic home, providing the gravitational stability that allows galaxies like ours to maintain their structure over billions of years. The story continues to unfold as we prepare to explore even more intriguing possibilities about what might be lurking in the dark spaces between the stars, and what recent discoveries about the nature of space and time might tell us about our cosmic future. But that's a journey for our next chapter in this cosmic mystery. But here's where our story takes a turn toward the truly mysterious. The space between us and these distant black holes isn't actually empty at all. It's alive with what quantum physicists call the vacuum energy, a restless sea of virtual particles popping into existence and vanishing again in timescales so brief they challenge our very notion of reality. Some interpretations suggest that this quantum foam might interact with black holes in ways we're only beginning to understand. Picture, if you will, the space around you right now. Every cubic centimetre contains enough vacuum energy that if we could somehow harness it, would power our civilization for millions of years. This energy isn't just theoretical, it creates measurable effects like the Casimir force, where two metal plates placed impossibly close together in a vacuum actually attract each other due to the pressure of virtual particles. Now imagine how this quantum activity might behave near a black hole, where space and time themselves are stretched and warped beyond recognition. The boundary between the quantum world and the gravitational realm becomes blurred, creating possibilities that seem to emerge from the realm of pure mathematics yet manifest as physical reality. Take a breath here and consider how this might change your perception of the emptiness around you. The space in your room, the air between your fingers, even the vacuum of space itself is alive with constant activity at scales too small and too brief for us to perceive directly. We exist not in emptiness, but in a cosmos humming with invisible energy. Recent theoretical work has proposed something even more intriguing: the possibility that microscopic primordial black holes, formed in the first moments after the Big Bang, might be passing through our solar system on a regular basis. These aren't the stellar mass giants we've been discussing, but objects with the mass of an asteroid compressed into a region smaller than an atom. The mathematics suggest that if such objects exist and account for even a fraction of dark matter, one might transit our inner solar system every decade or so. But here's the remarkable part. Such a passage would be almost entirely benign. The black hole would be so small that it would pass through Earth like a cosmic ghost, perhaps creating a microscopic tunnel 10 centimeters wide as it travels from one side of our planet to the other. This remains unproven, but the possibility illustrates something profound about the nature of our cosmic neighborhood. We might be sharing our space not just with distant stellar mass black holes, but with a hidden population of microscopic gravitational entities that regularly pass through our planet, our atmosphere, and perhaps even through our bodies without us ever knowing. Some researchers have suggested that we might be able to detect these passages through their gravitational effects on sensitive instruments, or even through the microscopic traces they might leave in very old rocks or glass. Some researchers have speculated about geological traces, such as tiny tunnels, that could hypothetically be linked to primordial black holes. The story of how we've come to understand our black hole neighbours is itself a meditation on the nature of knowledge and perception. These objects, by definition, emit no light. They are holes punched in the fabric of space-time itself, detectable only through their gravitational influence on the matter around them. The precision required to identify these invisible giants pushes our technology and our understanding to their absolute limits. When astronomers detected the subtle wobbles in the motion of the companion star to Gaia BH1, they were measuring movements so tiny that they required accuracy equivalent to detecting the width of a human hair from a distance of several miles. This level of precision emerges from decades of technological refinement, but also from something more fundamental: a deep trust in the mathematical description of gravity provided by Einstein's general relativity. We believe in the existence of these black holes not because we can see them directly, but because the mathematics predicts exactly the gravitational signatures we observe. As you listen, notice how this mirrors other aspects of knowledge in your own life. How often do we infer the existence of important but invisible things through their effects rather than direct observation? The love of a friend revealed through their actions, the health of an ecosystem shown through the behaviour of its inhabitants, the quality of our thinking demonstrated by the patterns of our choices. The detection of black holes also reveals something beautiful about the collaborative nature of modern science. The discovery of Gaia BH1 required the combined efforts of space-based telescopes, ground-based observatories, sophisticated data analysis algorithms, and teams of researchers working across continents and decades. No single instrument or individual could have made this discovery alone. Each new detection builds upon the previous ones, creating a growing map of our cosmic neighborhood that becomes more detailed and more surprising with each addition. The pattern that emerges suggests that black holes are not rare cosmic accidents, but fundamental features of the galactic landscape, as common as stars themselves but invisible to casual observation. The statistical extrapolations from our current detections paint a picture of a galaxy containing hundreds of millions of these objects, scattered throughout the spiral arms like invisible lighthouses marking the gravitational geography of our cosmic region. Some exist in binary systems like Gaia BH1, locked in eternal dances with stellar companions. Others wander alone through the interstellar medium, solitary travellers carrying the compressed memory of ancient stars. This brings us to a deeper question that extends beyond astronomy into the realm of philosophy and meaning. What does it mean to exist in a universe where unseen forces exist in the darkness between the stars? How do we find comfort and purpose in a cosmos that contains regions where matter disappears forever and time itself slows to a crawl? One perspective is that the presence of these black holes, rather than being threatening, actually represents a form of cosmic recycling. The matter that falls beyond their event horizons isn't destroyed in any conventional sense. It's transformed into something beyond our current understanding. Some interpretations suggest that black holes might be connected to other regions of space-time, or even other universes entirely, though this remains highly speculative, and no scientific consensus exists on such possibilities. The black holes in our neighbourhood also serve as natural laboratories for testing our most fundamental theories about the nature of reality. The extreme gravitational fields near their event horizons create conditions that cannot be replicated anywhere else in the accessible universe. By studying these objects, we probe the boundaries of physics itself. Consider the profound loneliness of a black hole. Once formed, it exists in a state of cosmic isolation, separated from the rest of the universe by its own event horizon. Information can flow in, but never out. It's a one-way membrane in space-time, creating a boundary between the knowable and the unknowable that persists for billions of years. Yet this isolation is not complete. Through Hawking radiation, black holes slowly evaporate, returning their mass energy to the universe over timescales so vast they dwarf the current age of the cosmos. The smallest black holes evaporate fastest, while the largest might persist long after the last stars have died and the universe has grown cold and dark. Take a moment to contemplate this cosmic timescale. The black holes in our neighbourhood will outlive not just our solar system, but our galaxy, our local group of galaxies, and perhaps even the fundamental particles that make up matter itself. They are, in a very real sense, among the most permanent features of the universe, monuments to stellar death that will persist long after everything we consider familiar has faded into the quantum foam. So how do we live with the knowledge that we share our cosmic neighbourhood with these invisible giants? How do we process the reality that somewhere within a few dozen light years of Earth, there might be a region of space-time so warped that time itself moves differently? Perhaps the answer lies not in fear, but in wonder. The existence of black holes reminds us that we inhabit a universe far stranger and more magnificent than our everyday experience suggests. We live in a cosmos where the extreme becomes commonplace, where the impossible is merely physics we don't yet fully understand. The protective vastness of space provides a natural buffer against these cosmic phenomena. Even if the closest black hole to Earth is only 40 light-years away, that distance represents a journey that would take our fastest spacecraft millions of years to complete. We exist in a cosmic bubble of safety, protected not by walls or barriers, but by the sheer scale of space and time. This scale also provides perspective on our own existence. Every atom in your body was forged in the nuclear furnace of an ancient star, some of which may have ended their lives as the very black holes we've been discussing. You are, quite literally, made of stardust that has travelled across cosmic time to assemble briefly into the pattern of consciousness that is reading these words. The carbon in your muscles, the iron in your blood, the calcium in your bones, all were created in stellar cores and scattered into space when those stars died. Some through gentle stellar winds, others through the massive stellar outbursts we call supernovae, and perhaps some through the formation of the black holes that now populate our galactic neighbourhood. This cosmic recycling continues around us constantly. The matter that falls into black holes doesn't simply disappear. It becomes part of a cosmic accounting system that we're only beginning to understand. Information, according to some interpretations of physics, cannot be truly destroyed, only transformed into forms that become increasingly difficult to decode. As you rest here, listening to this exploration of our cosmic neighbourhood, notice how the knowledge of nearby black holes might actually enhance rather than diminish your sense of connection to the universe. You exist not in a safe, predictable cosmos, but in one filled with mystery, beauty, and phenomena that challenge the very boundaries of human understanding. The story of our nearby black holes is still being written. As our detection methods become more sophisticated and our instruments more sensitive, we will undoubtedly discover many more of these invisible neighbours. The next generation of space-based gravitational wave detectors will be able to observe black hole mergers throughout the observable universe, while improved stellar surveys will identify the subtle gravitational signatures of black holes in binary systems we cannot currently detect. Within the next decade, we may have a complete census of every black hole within 100 light-years of Earth. This catalogue will transform our understanding of stellar evolution, the frequency of black hole formation, and the gravitational environment of our local stellar region. Future missions might even attempt to study nearby black holes directly, sending robotic probes to observe their effects on space and time from closer distances than ever before. While we cannot cross the event horizon and return to tell the tale, we can approach close enough to witness the extreme physics that occurs in the strong gravitational fields surrounding these objects. The technological challenges of such missions are immense but not necessarily insurmountable. A probe sent to study Gaia BH1, for example, would need to survive a journey of over 1,000 years, even using our most advanced propulsion concepts. Yet the scientific rewards would be extraordinary, providing direct measurements of how space and time behave under extreme gravitational stress. Some researchers have even proposed using nearby black holes as natural laboratories for testing exotic physics theories. The strong gravitational fields and high-energy environments around these objects might reveal new particles, new forces, or new symmetries in the fundamental laws of nature. As you imagine these future possibilities, consider how the presence of nearby black holes transforms from a source of cosmic anxiety into an opportunity for unprecedented scientific discovery. These invisible giants in our neighborhood represent not threats to be feared, but cosmic laboratories waiting to reveal their secrets to curious minds willing to look beyond the visible light of ordinary stars. The journey to understanding our place among these cosmic monsters has only just begun, and the discoveries that await us may reshape our understanding of reality itself in ways we cannot yet imagine. But the story of black holes near Earth is just one part of a much larger cosmic mystery. Recent discoveries in cosmology have begun to challenge some of our most fundamental assumptions about how the universe began, how it evolved, and where it might be heading. Revolutionary observations are forcing scientists to reconsider whether everything we thought we knew about the Big Bang might need to be completely rewritten. If you found this exploration of our cosmic neighborhood intriguing, you might be fascinated to learn about the mounting evidence that our standard model of cosmology may be fundamentally flawed. The next video in this series, Big Bang Theory is Wrong? Roger Penrose drops a bombshell, explores how one of the world's most respected physicists is proposing a radical, new vision of cosmic history that could overturn everything we thought we knew about the beginning of time itself. As we drift deeper into the cosmic night, there's another category of black holes that deserves our quiet contemplation: the rogue wanderers. These are black holes that have been ejected from their birthplaces, cast out into the darkness between stars, to wander the galaxy like cosmic nomads. They represent perhaps the most unsettling possibility in our neighborhood survey because they follow no predictable orbits, belong to no stellar systems, and could theoretically appear anywhere. Picture a black hole formed from the collapse of a massive star in a distant stellar nursery, then flung into space by the gravitational chaos of a multiple star system or the asymmetric explosion of its parent star. For millions or billions of years, it travels through the galaxy, an invisible wanderer carrying within its event horizon the compressed remains of ancient stellar matter. These rogue black holes are extraordinarily difficult to detect because they lack the stellar companions that reveal the presence of objects, like Gaia BH1. They emit no light, produce no easily observable effects, and drift silently through the interstellar medium like cosmic ghosts. We know they must exist. The physics of stellar evolution and galactic dynamics virtually guarantees their presence, but identifying them remains one of the greatest challenges in modern astronomy. Current estimates suggest there may be billions of these solitary travelers scattered throughout our galaxy. Some may have been wandering since the early epochs of star formation, carrying within them matter that predates the formation of our solar system. Others might be recent additions to the rogue population, ejected from their birth systems within the past few million years. The possibility that one of these wanderers might pass through our solar system provides both the ultimate test of our cosmic vulnerability and a reminder of the protective vastness of space. Even if a rogue black hole were detected heading toward us from the distance of our nearest stellar neighbour, Proxima Centauri, it would take thousands of years to arrive, assuming typical galactic velocities. As you contemplate this idea, notice how it changes your perception of the space around our solar system. What we often think of as empty void might actually be a highway for invisible travellers, objects so dense that a teaspoon of their material would outweigh Mount Everest, drifting silently past at distances we cannot yet detect. The statistical likelihood of such an encounter reminds us that while dramatic events are possible on cosmic timescales, they remain vanishingly rare on human ones. The probability of a rogue black hole passing close enough to disrupt Earth's orbit is estimated at roughly 1 chance in several million over the entire history of our planet. It's a reminder that we exist in a universe of both infinite possibility and protective improbability, but perhaps the most profound implications of nearby black holes lie not in their potential threat, but in what they might teach us about the fundamental nature of reality itself. These objects exist at the intersection of quantum mechanics and general relativity, two theories that have revolutionized our understanding of the universe, yet remain stubbornly difficult to reconcile with each other. Near the event horizon of a black hole, quantum effects become intertwined with gravitational ones in ways that challenge our most basic assumptions about information, causality, and the nature of space-time. Some interpretations suggest that the boundary of a black hole might not be a simple surface, but rather a complex quantum interface where information is processed in ways we cannot yet comprehend. The theoretical framework known as the holographic principle proposes something even more remarkable, that all the information contained within a volume of space might actually be encoded on its boundary. In the context of black holes, this suggests that everything that falls past the event horizon might continue to exist in some form on the black hole's surface, preserved in a quantum state that we cannot directly access. Take a moment to consider what this might mean for our understanding of existence itself. If the holographic principle is correct, then the black holes in our neighborhood are not simply cosmic vacuum cleaners, but rather cosmic information processors, maintaining perfect records of everything that has ever fallen into them across billions of years of galactic history. This remains highly speculative. No scientific consensus exists on the ultimate fate of information that crosses an event horizon, but the implications stretch far beyond academic physics. They touch on questions of memory, consciousness, and what it means for something to truly disappear from the universe. Recent work in quantum gravity has suggested that black holes might eventually return all the information they have absorbed through the process of Hawking radiation, but encoded in such a complex way that reconstructing the original information would be practically impossible. It's like burning a book and trying to reconstruct the text from the pattern of smoke and ash. Theoretically possible, but practically inconceivable. Yet this same universe has produced consciousness capable of contemplating its own existence. Through billions of years of stellar nuclear synthesis, cosmic evolution, and planetary development, matter has organized itself into patterns complex enough to ask questions about the nature of reality. You, listening to these words, represent one of the universe's ways of understanding itself. The black holes present in our cosmic vicinity serve as reminders that we inhabit not a tame, predictable cosmos, but one filled with mystery and wonder that extends far beyond our current understanding. Every new discovery, from the nearest stellar mass black hole to the possibility of primordial micro-black holes passing through our planet, reveals new layers of complexity in what we once thought we understood. Consider how this knowledge might change the way you experience a quiet evening under the stars. Knowing that invisible giants lurk in the darkness between the constellations doesn't diminish the beauty of the night sky. It enhances it. Each point of light becomes part of a cosmic dance that includes partners we cannot see, gravitational choreography that extends across scales from the quantum to the galactic. The protective vastness of space that keeps these cosmic monsters at safe distances also provides the arena for one of the most remarkable phenomena in the universe: the emergence of complexity from simplicity, of consciousness from matter, of questions from the very substance that composes the cosmos. As you rest here, breathing quietly in your small corner of the universe, you're surrounded by a cosmic environment more strange and wonderful than any science fiction has ever imagined. The atoms in your body carry the history of ancient stars, some of which may have ended their lives as the very black holes we've been discussing. You are, quite literally, the universe becoming conscious of itself. In these final moments of our exploration, let's return to that fundamental paradox with which we began. Objects so dark they emit no light, yet so influential they shape the very structure of space and time around them. The black holes in our neighborhood represent more than just exotic physics. They embody a profound truth about the nature of existence itself. Darkness and light, visible and invisible, known and unknowable, these apparent opposites dance together in the cosmic ballet that surrounds us. The black holes we cannot see define the gravitational landscape through which the stars we can see move and evolve. The invisible shapes the visible in ways both subtle and profound. This interplay between seen and unseen might serve as a metaphor for aspects of existence that extend far beyond astronomy. In your own life, notice how the invisible often shapes the visible, how the unspoken influences the spoken, how the unknown provides context for the known. The black holes in our galaxy remind us that reality extends far beyond what our senses can directly perceive. The journey we've taken together tonight, from the discovery of Gaia BH1 to the theoretical possibilities of quantum gravitational effects near event horizons, illustrates something beautiful about the human capacity for understanding. We can comprehend objects and phenomena that we will never directly experience, can map territories we will never visit, can find meaning in mysteries we may never fully solve. As you prepare to return to your daily existence, carry with you this sense of cosmic perspective. You live in a universe where black holes hide in the darkness between stars, where space itself can be warped beyond recognition, where time flows differently in different locations. Yet this same universe has produced the consciousness that is contemplating these ideas, the awareness that is capable of wonder. The black holes near Earth will continue their silent vigil long after our civilization has faded into cosmic history. They will outlive our sun, our galaxy, perhaps even the fundamental particles that make up matter itself. They are monuments to stellar death that will persist across timescales so vast they challenge human comprehension. But in this moment, in this brief flicker of cosmic time during which human consciousness has emerged to contemplate the universe, we have the privilege of knowing they are there. We can map their locations, study their properties, and find in their existence both humility and wonder. The darkness between the stars is not empty, it's alive with invisible giants, quantum fluctuations, and possibilities we have barely begun to explore. And somewhere in that darkness, perhaps closer than we dare imagine, cosmic monsters wait patiently in their gravitational lairs, bending space-time around themselves like cosmic hermits in caves made of warped geometry. Consider for a moment the concept of dark matter, that mysterious substance that comprises roughly 27% of the universe, yet interacts with ordinary matter almost exclusively through gravity. Recent theoretical work suggests that dark matter might not be uniformly distributed through space, but could form intricate structures, invisible highways, and dense knots that weave through our galaxy like a ghost architecture overlaying the visible cosmos. Some interpretations propose that primordial black holes, formed in the first moments after the Big Bang, might account for some portion of this dark matter. These objects could range in size from microscopic entities smaller than atoms to massive bodies rivaling traditional stellar mass black holes. If this speculative idea proves correct, our solar system might be swimming through a sea of invisible gravitational entities, most too small to notice individually, but collectively shaping the large-scale structure of our cosmic neighborhood. The mathematics of dark matter distribution suggest that Earth might be passing through dark matter streams, coherent flows of invisible particles that maintain their structure as they orbit the galactic center. These streams, if they exist, would be completely imperceptible to our senses, yet they would represent some of the most ancient structures in the universe, preserving patterns from the early epochs of cosmic evolution. As you contemplate this possibility, notice how it transforms your perception of the space around you. The room where you're listening, the air you're breathing, even the space between the atoms in your body might be permeated by invisible matter that predates the formation of our solar system. You could be, quite literally, swimming through the cosmic equivalent of an ancient river, feeling no current because you're part of the flow. Descending even deeper into the invisible architecture of space, we encounter phenomena that exist at the intersection of quantum mechanics and cosmology. At the smallest scales imaginable, far below the level of atoms or even subatomic particles, space itself becomes a seething foam of virtual particles and quantum fluctuations. This quantum foam, as physicists call it, represents the universe's way of dealing with the fundamental uncertainty that governs reality at its deepest level. Virtual particle pairs spontaneously appear from the vacuum, exist for impossibly brief moments, then annihilate each other and return to nothingness. This process happens everywhere, constantly, creating what some interpretations suggest might be the most energetic phenomenon in the cosmos, hidden beneath the apparent calm of empty space. The energy density of this quantum vacuum is so enormous that if we could somehow harness even a tiny fraction of it, we could power our civilization for millions of years. Yet this energy remains forever inaccessible, locked away by the fundamental laws of quantum mechanics in a cosmic savings account we can observe but never withdraw from. Near black holes, this quantum foam behaves in ways that stretch our understanding to its limits. The extreme curvature of spacetime around these objects might amplify certain quantum effects, while suppressing others, creating conditions that exist nowhere else in the accessible universe. Some theoretical frameworks suggest that the event horizons of black holes might serve as one-way membranes between different quantum states, allowing information to enter, but transforming it so completely that recovery becomes impossible. Take a breath here and consider how this quantum activity might relate to your own existence. Every atom in your body is surrounded by this invisible sea of virtual particles. The stability of matter itself depends on quantum processes that occur at scales so small they make atomic nuclei seem gigantic. You exist not in empty space, but in a cosmos alive with hidden activity at every level. One of the most profound implications of living in a galaxy populated with black holes relates to what astronomers call the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and our lack of contact with such civilizations. The presence of hundreds of millions of black holes scattered throughout our galaxy adds a sobering dimension to this cosmic mystery. Consider that any advanced civilization attempting to explore or colonize the galaxy would need to navigate through a gravitational minefield of invisible black holes. Unlike the hazards we're familiar with in our solar system, asteroids and comets that can be detected and avoided, black holes represent navigation threats that might remain undetected until it's too late to change course. A civilization launching interstellar missions would need to map not just the visible stars and planets along their intended routes, but also the invisible population of stellar mass and primordial black holes that might lurk in the darkness between star systems. The technical challenges of such mapping, requiring the kind of precision observations that we've only recently achieved in our own cosmic neighborhood, might represent a significant barrier to galactic expansion. This remains highly speculative, but it suggests one possible answer to why our galaxy appears so quiet, despite its apparent potential for hosting life. The cosmic monsters we've been discussing might serve as natural barriers to interstellar travel, creating isolated islands of civilization separated by vast regions of space containing hidden gravitational challenges. As you listen, imagine how this might change the way you think about our place in the cosmic community. We might not be alone in the galaxy, but rather part of a vast archipelago of isolated civilizations, each developing independently in the gravitational safe harbors around stable stars. separated by dark oceans, where black holes prowl like unseen wanderers. The longevity of black holes provides perhaps the most mind-bending perspective on cosmic time and the ultimate fate of everything we consider real. While stars burn out, planets cool and die, and even atomic nuclei eventually decay, black holes persist across timescales that challenge human comprehension. A black hole with the mass of our Sun would take approximately 10 to the 67th power years to evaporate through Hawking radiation. To put this in perspective, that's a number so large that if you wrote it out in standard notation, it would contain more digits than there are atoms in the observable universe. The current age of our cosmos, roughly 14 billion years, is utterly insignificant compared to the lifespan of even modest black holes. The supermassive black holes at the centers of galaxies will persist even longer, with evaporation times that dwarf stellar lifespans by factors that themselves require scientific notation to express. These objects will remain active long after the last stars have died, the last planets have been stripped from their orbits, and the universe has expanded and cooled to the point where new star formation becomes impossible. In the far future, billions of years after our Sun has swelled into a red giant and consumed the inner planets, the black holes in our neighborhood will continue their silent vigil. They will outlive our galaxy's collision with Andromeda, scheduled to occur in roughly 4.5 billion years. They will persist through the era when the universe has expanded so much that distant galaxies disappear beyond the cosmic horizon, leaving isolated galactic remnants floating in an increasingly empty cosmos. Picture yourself existing in such a far future, if consciousness could somehow persist across such vast timescales. The night sky would be nearly empty, with only a few nearby stars providing illumination. But the black holes would still be there, invisible anchors in space, slowly converting the last remaining matter into energy through processes so gradual they make geological time seem frantic. Perhaps no aspect of black holes challenges our understanding of reality more profoundly than the information paradox, a puzzle that sits at the intersection of quantum mechanics, general relativity, and the fundamental nature of existence itself. When matter falls past the event horizon of a black hole, what happens to the information that describes its quantum state? According to classical general relativity, that information disappears forever, swallowed by the black hole and sealed away beyond the event horizon, where no signal can ever escape. But quantum mechanics insists that information cannot be destroyed, only transformed or redistributed. This creates a fundamental conflict between two of our most successful theories about how the universe works. Some interpretations suggest that information falling into a black hole becomes encoded on its surface in a form so scrambled that reconstructing the original data would be practically impossible, even if theoretically feasible. It's like taking a library, burning all the books, and trying to recover the text from the precise pattern of smoke particles, heat distribution, and ash composition. The information is still there in principle, but accessing it requires capabilities beyond anything we can imagine. Other proposals involve even stranger possibilities. Some theoretical frameworks suggest that black holes might be connected to other regions of spacetime through invisible bridges called wormholes, allowing information to escape through pathways that bypass the event horizon entirely. This remains highly speculative, and no scientific consensus exists on whether such structures could exist in reality. As you contemplate these ideas, notice how they challenge our basic assumptions about permanence and loss. If information truly cannot be destroyed, then everything that has ever fallen into the black holes in our neighborhood continues to exist in some form, encoded in ways we cannot decipher, but preserved nonetheless according to the deepest laws of physics. The black holes scattered throughout our galactic neighborhood exist not as isolated objects, but as integral components of a vast cosmic web that connects every structure in the universe. Their gravitational influence help shape the large-scale distribution of matter, creating the scaffolding upon which galaxies, star clusters, and planetary systems form and evolve. This web extends far beyond gravity. The elements forged in the hearts of massive stars, then scattered into space when those stars collapse into black holes, become the raw materials for new generations of stars and planets. The carbon in your muscles, the iron in your blood, and the calcium in your bones all participated in this cosmic recycling process, possibly multiple times across billions of years of galactic evolution. In this sense, the black holes in our neighborhood are not separate from us, but part of our extended cosmic ancestry. They represent the final fate of some of the very stars that created the heavy elements essential for life as we know it. Knowing that invisible giants exist between the constellations are, paradoxically, among our most distant relatives in the great family tree of cosmic evolution. Consider how this perspective might change your relationship to the night sky. Those points of light you see aren't just distant suns, but active participants in a vast network of creation and destruction that spans the galaxy. The black holes you cannot see are equally important nodes in this network, processing matter and energy according to laws we're still learning to understand. This cosmic web also operates on scales of time that dwarf human experience. The black holes near Earth have been shaping their local environments for millions or billions of years, influencing the orbits of nearby stars, triggering episodes of star formation, and gradually altering the gravitational landscape of our galactic region. As we approach the end of our journey through the dark neighborhoods of our galaxy, it's worth reflecting on what the study of black holes reveals about the nature of consciousness itself. These objects exist at the absolute limits of what we can observe and understand. Yet through mathematics, careful observation, and theoretical reasoning, we've managed to map their locations and properties with remarkable precision. The human mind's ability to comprehend objects and phenomena that exist beyond direct experience represents one of the most extraordinary capabilities in the known universe. We can visualize regions where time slows to a crawl, understand the behavior of matter compressed to infinite density, and predict the evolution of objects across timescales that exceed the age of the cosmos by factors of trillions. This capacity for abstract understanding might itself represent a kind of cosmic phenomenon worth contemplating. Through billions of years of stellar nucleosynthesis and planetary evolution, matter has organized itself into patterns capable of comprehending the very processes that created it. The atoms in your brain, forged in ancient stellar cores, now contemplate the black holes that represent the final fate of similar stars. Some interpretations suggest, though this remains highly speculative, that consciousness might play a fundamental role in the quantum processes that govern reality at its deepest level. The act of observation appears to influence quantum systems, though the mechanism and implications of this influence remain hotly debated among physicists. No scientific consensus exists on whether consciousness has any special status in quantum mechanics, but the question continues to generate fascinating theoretical work. As you rest here, contemplating these invisible giants in our cosmic neighborhood, you're participating in one of the universe's most remarkable achievements, matter becoming aware of itself. The same gravitational processes that create black holes also shape the cosmic environment that allowed planets to form, life to emerge, and consciousness to develop. The story of black holes near Earth ultimately illustrates something profound about the nature of scale in our universe. These objects, despite their incredible mass and gravitational influence, occupy regions of space smaller than most cities. A black hole with 10 times the mass of our Sun would have an event horizon only about 60 kilometers in diameter, yet its gravitational influence shapes the behavior of objects across distances measured in light years. This compression of enormous influence into tiny volumes represents one of the most extreme examples of efficiency in the natural world. Black holes achieve maximum gravitational impact with minimum spatial footprint, creating what might be considered the universe's most elegant solution to the problem of how to store vast amounts of mass energy in the smallest possible space. The contrast between the cosmic significance of these objects and their relatively modest physical size offers a lesson that extends beyond astronomy. In your own life, notice how small actions or decisions can sometimes have influences that propagate far beyond their apparent scale. A moment of kindness, a single insight, or a small change in perspective can create ripple effects that extend across years or even generations. The mathematics that describe black holes also reveal something beautiful about the underlying unity of natural law. The same equations that govern the fall of an apple from a tree also predict the behavior of matter spiraling into a black hole at speeds approaching that of light. The same quantum principles that determine the color of flowers also describe the radiation that black holes emit as they slowly evaporate across cosmic time. This unity suggests that despite the vast scales involved, from quantum foam to galactic superclusters, we inhabit a cosmos governed by laws that maintain their consistency across every level of reality. The black holes in our neighborhood follow the same fundamental principles that govern the atoms in your body, just expressed under more extreme conditions. Perhaps the greatest gift that knowledge of nearby black holes provides is perspective on our own existence. We live on a small planet orbiting an ordinary star in the outer regions of a typical galaxy, surrounded by invisible gravitational giants that we've only recently learned to detect. This situation is simultaneously humbling and extraordinary. The humbling aspect is obvious. We exist at the mercy of cosmic forces vastly more powerful than anything human civilization has ever produced or controlled. A rogue black hole passing through our solar system would significantly alter the solar system's dynamics, not through intent but through gravitational law, yet the extraordinary aspect is equally significant. In a universe filled with such overwhelming forces, matter has somehow organized itself into patterns capable of understanding and appreciating the very phenomena that could destroy it. You represent one of the cosmos' ways of knowing itself, a temporary arrangement of atoms that can contemplate infinity and find meaning in mystery. This perspective might change how you experience ordinary moments. The warmth of sunlight on your skin becomes more precious when you know it's generated by nuclear fusion in a star that will eventually exhaust its fuel and either fade away or collapse into one of the black holes we've been discussing. The air you breathe contains elements forged in stellar cores billions of years ago, then scattered into space by processes we're only beginning to understand. The safety and stability of our current cosmic environment, protected by vast distances from the nearest black holes, represents a temporary gift of cosmic time and space. It's a brief window during which consciousness has emerged to witness and wonder at the universe that created it. As our exploration draws toward its close, it's important to acknowledge how much we still don't know about the black holes in our neighborhood. Despite remarkable advances in detection methods and theoretical understanding, these objects remain among the most mysterious phenomena in the cosmos. We don't know how many stellar mass black holes exist within 100 light-years of Earth. We can't detect isolated black holes that lack stellar companions. We have only theoretical models for how primordial black holes might behave if they exist. We don't understand what happens to information that falls past an event horizon. We can't predict when or where the next nearby black hole will be discovered. This ignorance isn't a failure of science, but rather an indication of how much wonder remains in the universe. Each new discovery about black holes generates more questions than it answers, opening up fresh avenues for investigation and contemplation. The mystery deepens even as our knowledge expands, like walking into a vast library where every book you read reveals the existence of countless more volumes waiting to be explored. Future generations will undoubtedly know things about black holes that we can barely imagine today. They might develop technologies for studying these objects directly, create artificial black holes for research purposes, or even discover that black holes play roles in cosmic processes we haven't yet conceived. The story we've told tonight represents just one chapter in humanity's ongoing relationship with these cosmic enigmas. As you drift towards sleep, carry with you this sense of participating in an unfinished story. The black holes in our neighborhood will continue their silent vigil long after our civilization has faded into history. But right now, in this moment, you're part of the brief cosmic episode during which matter has become conscious enough to wonder about its own fate. In these final moments of our cosmic journey, let's return to that fundamental mystery that has guided our exploration, the dance between the visible and invisible, the known and unknowable that defines our relationship with the universe. The black holes scattered through our galactic neighborhood represent the ultimate expression of this dance, objects so influential they shape the very structure of space and time. Yet so elusive, they remain hidden from direct observation. This dance between seen and unseen extends far beyond astronomy into the deepest questions about existence itself. In your own life, notice how much depends on things you cannot directly perceive. The thoughts of others, the quantum processes that maintain the stability of matter, the gravitational forces that keep your feet planted on the ground. The invisible shapes the visible in ways both profound and subtle, just as black holes influence the evolution of their stellar neighborhoods while remaining forever hidden from view. The protective vastness that keeps these cosmic monsters at safe distances also provides the arena for one of the universe's most remarkable achievements: the emergence of consciousness from matter, of questions from the very substance that composes the cosmos. You exist in a brief window of cosmic time when the universe has become complex enough to contemplate itself, when arrangements of atoms can wonder about the nature of space and time. The black holes in our neighborhood serve as reminders that we inhabit not a tame, predictable cosmos, but one filled with mystery and wonder that extends far beyond our current understanding. They challenge our assumptions about permanence and impermanence, about what it means for something to exist beyond the reach of observation, about the ultimate fate of information and matter in a universe governed by laws we're still learning to comprehend. As you rest here in the quiet darkness, breathing slowly and steadily, you're surrounded by a cosmic environment more strange and magnificent than any science fiction has ever imagined. The atoms in your body carry the history of ancient stars, some of which may have ended their lives as the very black holes we've been discussing. You are quite literally made of stardust, temporarily organized into the pattern of consciousness that is contemplating these words. The journey we've taken together tonight, from the discovery of our nearest black hole neighbors to the deepest questions about the nature of reality itself, illustrates something beautiful about the human capacity for wonder. We can find meaning in mystery, beauty in the unknown, and connection in the vastness that might otherwise seem isolating. The black holes near Earth will outlive our sun, our galaxy, perhaps even the fundamental particles that make up ordinary matter. They are monuments to stellar death that will persist across timescales so vast they challenge human comprehension. Yet in this moment, in this brief flicker of cosmic time during which consciousness has emerged to contemplate the universe, we have the privilege of knowing they are there. The darkness between the stars is not empty, but alive with invisible giants, quantum fluctuations, and possibilities we have barely begun to explore. As you drift towards sleep, let this knowledge settle gently into your consciousness. You exist in a universe where the impossible has become commonplace, where the extreme has become natural, where consciousness has emerged to witness wonders that exceed the boundaries of imagination. Sweet dreams, fellow traveller. You are part of something truly magnificent, a cosmos where matter has learned to contemplate infinity and find beauty in the dance between light and darkness, between the known and the forever unknowable. The black holes in our neighborhood wait patiently in their gravitational layers, bending space-time around themselves like cosmic hermits in caves made of warped geometry. They remind us that reality extends far beyond what our senses can perceive, that the universe is under no obligation to match our expectations, and that the most profound truths often hide in the spaces between what we can see and what we can imagine. Rest well, knowing that you're floating through a galaxy populated with invisible wonders, protected by the vast scales of space and time that keep cosmic catastrophe at comfortable distances, yet close enough to these mysterious objects to feel the thrill of living on the edge of the truly unknown. Tomorrow, when you wake and return to the familiar rhythms of daily life, you'll carry with you the quiet knowledge that somewhere in the darkness between the stars, cosmic monsters wait in silence, neither threatening nor comforting, simply existing as reminders that the universe is far stranger and more wonderful than we have yet learned to appreciate. And as you ponder these cosmic mysteries, you might find yourself wondering about even more fundamental questions that challenge everything we think we know about existence itself. How did this magnificent, mysterious universe come to be? What if our most basic assumptions about cosmic origins are completely wrong? What if the story of creation itself needs to be rewritten from the very beginning? The black holes scattered through our cosmic neighborhood carry within them something profoundly moving. The compressed memories of ancient stars that once illuminated regions of space we'll never see. Each of these invisible giants represents not just a gravitational anomaly, but a cosmic gravestone, marking the final chapter of a stellar life that may have burned brightly for millions or billions of years. Picture the star that eventually became Gaia BH1, our nearest known black hole neighbor. Long before our solar system even existed, this massive star was already middle-aged, fusing hydrogen into helium in its core, radiating energy across dozens of light-years of space. It may have hosted planets, warmed asteroids, and provided the energy that could have supported life in ways we can't imagine. For eons, it was a beacon of light and warmth in what is now the constellation Ophiuchus. But massive stars live fast and die young in cosmic terms. As this ancient star exhausted its nuclear fuel, it began a death spiral that would have been visible across vast stretches of the galaxy. The outer layers expanded into a red supergiant, possibly engulfing any worlds that orbited too closely. Then came the final collapse, an extremely powerful stellar implosion, so violent it created a gravitational field from which not even light can escape. As you rest here, contemplating this cosmic life cycle, notice how it mirrors patterns of creation and destruction that appear throughout nature. The death of massive stars seeds the galaxy with heavy elements essential for planet formation and life itself. The carbon in your muscles, the iron in your blood, all were forged in the nuclear furnaces of stars that died long before our sun was born. In a very real sense, you are the universe's way of remembering its own stellar ancestry. The process by which massive stars become black holes remains one of the most dramatic events in cosmic physics. During the final seconds of collapse, the star's core temperature reaches billions of degrees, hot enough to forge elements that exist nowhere else in nature. The gravitational field becomes so intense that space and time themselves begin to warp beyond recognition. Theoretical models suggest that the transition from star to black hole happens with almost incomprehensible violence. The outer layers of the star explode outward in a supernova blast that can outshine entire galaxies for weeks or months. Meanwhile, the core continues its relentless collapse, compressing matter to densities so extreme that a teaspoon of the material would weigh as much as a mountain. What emerges from this cosmic catastrophe is something that challenges our basic understanding of existence. The collapsed star becomes a region where the normal rules of physics break down, where matter disappears behind an event horizon that serves as a one-way boundary between the knowable and unknowable universe. It's as if nature has created cosmic filing cabinets where information can be stored but never retrieved. The gravitational influence of nearby black holes extends far beyond their immediate vicinity, creating invisible threads that connect distant regions of our galaxy in ways that shape the evolution of entire stellar populations. These connections operate across timescales so vast they make human history seem like a brief flicker, yet they influence the cosmic environment in which our own solar system formed and continues to evolve. Consider how the presence of Gaia BH1 affects the gravitational landscape of its stellar neighborhood. Stars passing within several light years of this invisible giant experience subtle perturbations in their orbits, changes so small they might accumulate over millions of years before becoming noticeable. Some stars may be nudged into slightly different trajectories, altering their encounters with gas clouds and affecting their rates of stellar formation. These gravitational influences create what astronomers call dynamical evolution, a slow-motion cosmic dance where the positions and velocities of stars gradually change through their mutual gravitational interactions. The black holes scattered through our galaxy serve as massive, invisible partners in this dance, their presence felt even when they can't be seen. The mathematical models that describe these interactions reveal something beautiful about the underlying order in apparent cosmic chaos. Despite the random nature of individual stellar encounters, the overall statistical behavior of stellar populations follows predictable patterns. It's as if the galaxy maintains a kind of gravitational memory, where the cumulative effects of countless small interactions create large-scale structure and organization. As you listen, take a moment to consider how this might relate to patterns in your own experience. Notice how small, seemingly random events in your life sometimes connect in unexpected ways over long periods, creating meaningful patterns that only become visible when viewed from sufficient distance in time. The cosmic dance of stellar evolution might mirror the subtle ways that individual moments and decisions weave together to create the larger story of existence. The presence of black holes also affects the chemical evolution of galaxies. When massive stars explode as supernovae before collapsing into black holes, they scatter heavy elements throughout the interstellar medium. These elements become incorporated into the next generation of stars and planets, creating an ongoing cycle of cosmic recycling that has operated since the early epochs of galactic history. Some of the oxygen you're breathing right now was forged in the core of a massive star that eventually became a black hole. The calcium in your bones, the iron in your blood, all participated in this cosmic recycling process. You exist as part of an unbroken chain of stellar nucleosynthesis that connects you directly to the black holes lurking in our galactic neighborhood. Perhaps no aspect of nearby black holes challenges human understanding more profoundly than their relationship to the fundamental limits of what can be known. These objects exist at the boundary between the observable universe and regions that are forever beyond the reach of any signal, any information, any form of communication or investigation. When matter falls past the event horizon of a black hole, it doesn't simply disappear in the way we normally understand disappearance. Instead, it enters a region of space-time that becomes disconnected from the rest of the universe in the most absolute sense possible. No light, no radio waves, no gravitational signals can carry information about what happens beyond that boundary back to the outside world. This creates what philosophers of science call an epistemological boundary, a fundamental limit to what conscious beings can know about reality. It's different from practical limitations, like not having powerful enough telescopes or fast enough computers. The event horizons of black holes represent theoretical limits written into the basic structure of space-time itself. Yet these boundaries might not be as absolute as they first appear. Recent theoretical work in quantum gravity suggests that the classical picture of event horizons as perfect one-way membranes might be oversimplified. Some interpretations propose that information falling into black holes becomes encoded in quantum correlations that extend across the boundary, preserving a kind of shadow of the original information in forms that might, in principle, be recoverable. This remains highly speculative, with no scientific consensus on whether such quantum effects actually allow information to escape from black holes. But the possibility illustrates something profound about the relationship between knowledge and reality. Even when faced with absolute barriers to direct observation, human consciousness finds ways to probe the edges of the unknowable through mathematics, theoretical reasoning, and careful logical analysis. As you contemplate these ideas, notice how they might relate to boundaries and limitations in your own experience of knowledge. Consider the aspects of existence that remain mysterious despite our best efforts to understand them. The nature of consciousness itself, the experience of others, the deeper meaning of coincidence and pattern in daily life. Like black holes, these phenomena exist at the edges of what can be directly observed or measured, yet they profoundly influence our understanding of what it means to exist. The study of black holes teaches us something valuable about living with uncertainty and mystery. Rather than being frustrated by the limits of knowledge, we can find meaning in the questions themselves, beauty in the boundaries between known and unknown, wonder in the recognition that reality extends far beyond what consciousness can directly access. The existence of black holes in our galactic neighborhood sets in motion cascades of consequences that rip ways that connect pull through space and time in the largest scales of cosmic structure to the smallest details of planetary evolution. These consequences unfold across timescales that span from microseconds to billions of years, creating a complex web of cause and effect that shapes the environment in which life emerges and evolves. Consider the role that nearby black holes play in regulating star formation throughout our region of the galaxy. Their gravitational influence affects the distribution and motion of interstellar gas clouds, the raw material from which new stars are born. Regions where black holes have cleared out material may experience reduced rates of star formation, while other areas where gas has been compressed by gravitational interactions may see bursts of stellar birth. These variations in star formation rates influence the chemical composition of subsequent stellar generations. Stars born in different regions and at different times inherit different mixtures of heavy elements, affecting everything from their lifespans to their likelihood of hosting planets capable of supporting life. The black holes in our neighborhood thus play an indirect but significant role in determining the cosmic conditions that made our own existence possible. The gravitational waves produced when black holes spiral into each other and merge represent another form of cosmic consequence that connects our local environment to the broader universe. These ripples in space-time carry energy and information across vast distances, subtly affecting the motion of matter throughout the galaxy. The recent detection of gravitational waves by observatories like LIGO has opened an entirely new window into the black hole population of our cosmic neighborhood. Each gravitational wave event that we detect represents the final moments in the billion-year death spiral of two massive objects, often black holes that formed from ancient stars and eventually found each other across the vastness of space. The energy released in these mergers can exceed the combined light output of all the stars in the observable universe, yet it passes through our detectors as whisper-soft distortions in the fabric of space-time itself. As you rest here, breathing slowly and steadily, take a moment to appreciate that your body is constantly being traversed by these gravitational waves from distant cosmic catastrophes. The space between the atoms in your cells expands and contracts by amounts smaller than a fraction of a proton's width as these waves pass through, carrying information about black hole collisions that occurred billions of years ago in distant corners of the universe. This constant bath of gravitational radiation creates a kind of cosmic background music, inaudible to our ears but detectable by our most sensitive instruments. Some interpretations suggest, though this remains unproven, that this gravitational symphony might provide clues about the fundamental structure of space-time itself, possibly revealing whether reality is continuous or quantized at its deepest level. The black holes scattered through our cosmic neighborhood raise profound philosophical questions about the nature of existence, presence, and reality that extend far beyond the boundaries of physics and astronomy. What does it mean for something to exist if it can never be directly observed? How do we reconcile the undeniable influence of these objects with their fundamental invisibility? What can invisible presence teach us about the nature of meaning and significance in our own lives? These questions have occupied philosophers and scientists for decades, creating a rich dialogue between empirical observation and theoretical reasoning. The black holes near Earth exist in a strange category of phenomena that are simultaneously absolutely real and absolutely unobservable. We know they're there because of their effects on visible matter, yet they remain forever hidden behind event horizons that prevent any direct contact or communication. This situation creates what philosophers call an ontological puzzle. If something influences the world around it but cannot itself be observed, what kind of existence does it have? The answer might depend on how we define existence itself. If existence requires only the ability to affect other things, then black holes clearly exist. If it requires the possibility of direct observation, their status becomes more ambiguous. Some interpretations suggest that the distinction between visible and invisible might be less fundamental than it appears. From the perspective of quantum mechanics, all particles exist as probability distributions until they're observed. In this view, the event horizon of a black hole might simply represent an extreme case of the more general principle that reality emerges from the interaction between consciousness and the quantum substrate that underlies all phenomena. This remains highly speculative, and no scientific consensus exists on whether consciousness plays any special role in quantum mechanics. But the possibility illustrates how the study of black holes pushes us toward the deepest questions about the relationship between mind and matter, observation and reality, knowledge and existence. As you contemplate these ideas, notice how they might relate to invisible influences in your own experience. Consider the impact of unspoken thoughts, unexpressed emotions, or subtle atmospheric shifts that affect your mood and behavior in ways you might not consciously recognize. Like black holes, these invisible aspects of experience shape the visible world while remaining largely hidden from direct observation. The presence of nearby black holes might serve as a cosmic metaphor for all the hidden forces that influence our lives, the unconscious patterns that guide our decisions, the cultural assumptions that shape our perceptions, the quantum processes that maintain the stability of matter itself. Reality, it seems, is largely invisible, with the visible world representing only the tip of a much larger iceberg of existence. The methods we use to detect black holes in our cosmic neighborhood represent one of the most elegant examples of what might be called the poetry of inference, the art of discovering invisible truths through careful observation of visible effects. These techniques push the boundaries of both technology and human reasoning, creating tools that can reveal the presence of objects that emit no light and send no signals. The discovery of Gaia BH1, our nearest known black hole, required the combined precision of space-based telescopes and ground-based observatories working together across years of careful measurement. The European Space Agency's Gaia telescope monitored the positions and motions of over 1 billion stars with accuracy measured in micro-arc seconds, detecting wobbles so subtle they would be invisible to any Earth-based observer. These wobbles, caused by the gravitational influence of an invisible companion, told a story written in the language of orbital mechanics. By analysing the precise timing and amplitude of the companion star's motion, astronomers could infer not only the presence of the black hole, but also its mass, orbital period, and distance from Earth. It's detective work on a cosmic scale, following gravitational breadcrumbs to reveal the presence of invisible suspects. The mathematics required for these calculations builds upon centuries of theoretical development. From Newton's laws of gravitation to Einstein's general relativity to modern computational techniques that can model the complex gravitational interactions between multiple objects over long periods of time. Each discovery represents not just a single observation, but the culmination of humanity's evolving understanding of how gravity works across all scales. Consider the remarkable chain of reasoning that leads from tiny stellar wobbles to confident assertions about the existence of specific black holes at precise distances. This process requires faith not just in our instruments, but in the mathematical frameworks we use to interpret their data. We believe in these invisible giants because the equations predict exactly the observable effects we measure. As you listen, take a moment to appreciate the extraordinary precision required for these detections. The motions that reveal nearby black holes are so small that they would be completely overwhelmed by the thermal expansion of our telescope mirrors due to temperature changes throughout the day. The fact that we can extract meaningful signals from such noisy data represents a triumph of both engineering and statistical analysis. The technology of black hole detection also illustrates something beautiful about the collaborative nature of modern science. No single instrument or technique can reveal these objects alone. Instead, their discovery requires the coordination of space missions, ground-based observatories, theoretical calculations, and data analysis techniques developed by researchers across multiple continents and decades. As our detection methods become more sophisticated and our instruments more sensitive, we stand on the threshold of what might be called an archaeological expedition into the invisible architecture of our galactic neighborhood. The next generation of telescopes and gravitational wave detectors will allow us to map the black hole population of our cosmic region with unprecedented completeness and precision. The European Space Agency's upcoming LISA mission, scheduled for launch in the 2030s, will deploy a constellation of spacecraft designed to detect gravitational waves from space. Unlike ground-based detectors that are limited by seismic noise and other terrestrial interference, LISA will be sensitive to a much broader range of gravitational wave frequencies, potentially revealing black hole mergers and interactions that are currently invisible to our instruments. This space-based gravitational wave observatory might detect dozens or hundreds of black hole systems within our local galactic region, providing the first comprehensive census of these invisible neighbors. Each detection will add another piece to the puzzle of how black holes form, evolve, and influence their cosmic environments over billions of years. Future ground-based telescopes with mirrors spanning dozens of meters and equipped with adaptive optics systems that can compensate for atmospheric turbulence in real time will be able to detect the subtle gravitational influences of much smaller and more distant black holes. These instruments might reveal isolated black holes that lack stellar companions, objects that remain completely invisible to current detection methods. The combination of these advancing technologies might transform our understanding of the black hole population from statistical estimates to detailed maps showing the location, mass, and orbital characteristics of individual objects throughout our cosmic neighborhood. Within your lifetime, we might have catalogues listing every black hole within 100 light-years of Earth, complete with predictions of their future evolutionary paths. As you contemplate these future possibilities, consider how they might change our relationship to the night sky. Knowing the precise locations of invisible giants scattered between the visible stars could transform stargazing from a simple appreciation of distant lights into a complex awareness of the gravitational landscape that surrounds us. Imagine looking up at the constellation Ophiuchus and knowing exactly where Gaia BH1 lurks among the visible stars, its presence marked not by light but by our understanding of the mathematics that govern its behaviour. Future generations might develop augmented reality systems that overlay the positions of nearby black holes onto the night sky, creating a kind of cosmic X-ray vision that reveals the invisible architecture underlying the visible universe. Perhaps no aspect of nearby black holes challenges human perspective more profoundly than their relationship to time itself. These objects exist not just as features of our current cosmic environment, but as bridges connecting the deepest past to the furthest future, carrying within their event horizons information about stellar processes that occurred billions of years ago while persisting across timescales that extend far beyond anything we can easily comprehend. The black hole that became Gaia BH1 formed from the collapse of a massive star that lived and died while our solar system was still a cloud of gas and dust orbiting the early sun. The light from that star's final supernova explosion may have illuminated regions of space that no conscious being ever witnessed, creating a brief spectacular display in the cosmic darkness before fading into the background radiation that still permeates the galaxy. Yet the gravitational field created by that ancient stellar collapse continues to influence the motion of matter today, 1,560 years after the light from its companion star began its journey toward Earth. In a very real sense, we are observing the present-day consequences of events that occurred in the deep cosmic past, seeing how ancient stellar deaths continue to shape the gravitational landscape of our galactic neighbourhood. This temporal connection between past and present extends to the fundamental physics of black hole behaviour. According to general relativity, time itself slows down in strong gravitational fields, creating effects that become extreme near black hole event horizons. An observer watching matter fall into a black hole would see it slow down and freeze at the event horizon, appearing to hover there forever, while growing redder and dimmer as its light is stretched by the gravitational field. From the perspective of the falling matter itself, however, the journey across the event horizon would seem to take only a finite amount of time. This creates a kind of temporal paradox, where events appear to take both forever and an instant, depending on your point of view. It's as if black holes exist at the intersection of different temporal realities, each equally valid but incompatible with the others. As you rest here, breathing slowly and contemplating these temporal mysteries, notice how your own experience exists at the intersection of different timescales. Your heartbeat marks seconds and minutes. Your thoughts flow across moments and hours. Your memories connect days and years, while your existence as a conscious being spans decades in a universe that has evolved across billions of years. The atoms in your body have their own temporal stories forged in stellar cores across cosmic time, scattered by ancient supernovae, incorporated into the molecular machinery of life through processes that operate on timescales ranging from nanoseconds to geological epochs. You exist as a temporary pattern in matter that has been cycling through stars, planets, and living beings for billions of years. The black holes scattered throughout our cosmic neighbourhood participate in what might be described as a vast cosmic symphony, a complex interplay of gravitational influences that shapes the evolution of stellar systems across our entire region of the galaxy. This symphony operates on scales both spatial and temporal that dwarf human experience, yet it creates the cosmic environment in which our own solar system formed and continues to evolve. Each black hole contributes its own gravitational voice to this cosmic composition. The massive presence of objects like Gaia BH1 creates standing waves in the distribution of interstellar matter, regions where gas and dust collect, and others where they're swept away by tidal forces. These patterns influence where new stars form and how existing stellar systems evolve over millions of years. The mathematics that describe these interactions reveal something beautiful about the underlying order in apparent cosmic chaos. Despite the complex, seemingly random nature of individual gravitational encounters, the overall behavior of stellar populations follows statistical patterns that can be predicted and understood. It's as if the galaxy maintains a kind of gravitational memory, where the cumulative effects of countless small interactions create large-scale structure and organization. Recent computer simulations of galactic evolution suggest that the presence of black holes throughout the galaxy creates a kind of cosmic metabolism, regulating the rate at which gas clouds collapse to form new stars and determining how heavy elements are distributed through the interstellar medium. Without these invisible gravitational anchors, the galaxy might evolve very differently, possibly in ways that would be less favorable for the formation of planetary systems capable of supporting life. The gravitational waves produced by black hole mergers add another layer to this cosmic symphony. These ripples in space-time carry energy and momentum across vast distances, subtly affecting the motion of matter throughout the galaxy. Each merger event sends gravitational signals that propagate outward at the speed of light, creating interference patterns that influence the behavior of other massive objects they encounter along the way. As you listen to these ideas, take a moment to appreciate that you're currently immersed in this gravitational symphony. The space around your body is continuously being traversed by gravitational waves from distant black hole mergers, creating infinitesimal expansions and contractions in the distance between atoms. These effects are far too small to feel, but they represent your direct physical connection to cosmic events occurring across the galaxy. Some interpretations suggest, though this remains highly speculative, that the constant background of gravitational waves might influence the evolution of complex systems in subtle ways, possibly affecting everything from the formation of planetary atmospheres to the development of life itself. No scientific consensus exists on such possibilities, but they illustrate how the invisible influences of distant black holes might extend into the most intimate details of existence. The regions between stars, often dismissed as empty void, actually teem with activity and structure that connects our solar system to the broader galactic environment in ways we're only beginning to understand. The black holes scattered through our cosmic neighborhood play crucial roles in shaping this interstellar ecology, creating currents and patterns in the distribution of matter and energy that influence the evolution of entire stellar regions. Consider the interstellar medium, the thin gas that fills the space between stars throughout our galaxy. This material, composed primarily of hydrogen and helium with traces of heavier elements, exists at densities so low that it would qualify as a perfect vacuum by Earth standards. Yet across the vast scales of interstellar space, this tenuous medium contains more mass than all the visible stars combined. The gravitational influence of nearby black holes shapes the flow and distribution of this interstellar material in complex ways. Their presence creates what astronomers call gravitational focusing effects, where streams of gas and dust are deflected and concentrated into patterns that can persist for millions of years. These patterns influence where and when new stars form, affecting the chemical composition and evolutionary paths of entire stellar generations. The magnetic fields that thread through the interstellar medium add another layer of complexity to this cosmic ecology. These fields, generated by the rotation of the galaxy and the motion of charged particles, interact with the gravitational influences of black holes to create structures that can channel matter and energy across vast distances. Some researchers have proposed that these magnetic gravitational interactions might create a kind of galactic nervous system, connecting distant regions through networks of flowing plasma and electromagnetic fields. As you contemplate this invisible ecosystem that surrounds our solar system, notice how it challenges the common perception of space as empty and lifeless. Instead of being isolated on a small planet in a vast void, we exist within a dynamic, interconnected environment where matter and energy flow in patterns shaped by forces operating on scales from quantum to galactic. The solar wind produced by our own sun interacts with this interstellar environment, creating a protective bubble called the heliosphere that shields our planetary system from some forms of cosmic radiation. This bubble is not static, but responds to changes in the interstellar medium, expanding and contracting as our solar system moves through regions of varying density and magnetic field strength. Recent discoveries have revealed that our solar system is currently passing through a region of space called the local interstellar cloud, a relatively dense concentration of gas and dust that may have been shaped by ancient supernova explosions and the gravitational influences of nearby massive objects. This cloud affects everything from the intensity of cosmic rays reaching Earth to the behavior of the outer boundaries of our solar system. At the smallest scales imaginable, the space between us and the nearest black holes seethes with quantum activity that connects every point in the universe through invisible networks of virtual particles and fluctuating fields. This quantum foam, as physicists call it, represents perhaps the most fundamental level of cosmic ecology, where the boundaries between existence and non-existence become blurred in ways that challenge our most basic assumptions about reality. The vacuum energy that fills all of space creates what some interpretations describe as a kind of cosmic background consciousness, though this remains highly speculative and no scientific consensus exists on whether quantum fields have any relationship to awareness or information processing. What we do know is that this quantum activity influences the behavior of matter and energy in measurable ways, from the stability of atoms to the expansion rate of the universe itself. Near black holes, these quantum effects become amplified in ways that push the boundaries of our understanding. The extreme curvature of space-time around these objects might create conditions where virtual particles become real, where the vacuum itself begins to radiate energy, and where the normal distinctions between matter and empty space break down entirely. The theoretical framework, known as Hawking radiation, suggests that black holes slowly evaporate by emitting particles created from quantum fluctuations near their event horizons. This process would cause even the largest black holes to eventually disappear, though the time-esque. Chapter 36. The Quantum Whispers Between the Stars. Continued. The theoretical framework known as Hawking radiation suggests that black holes slowly evaporate by emitting particles created from quantum fluctuations near their event horizons. This process would cause even the largest black holes to eventually disappear, though the timescales involved are so vast they dwarf the current age of the universe by factors that challenge human comprehension. A black hole with the mass of our Sun would take longer to evaporate than it would take for every star in the galaxy to burn out and die. Yet this quantum connection between the smallest and largest scales in physics hints at something profound about the underlying unity of natural law. The same uncertainty principles that govern the behavior of subatomic particles also determine the ultimate fate of the most massive objects in the universe. It's as if reality maintains a kind of cosmic accounting system where information and energy can be transformed but never truly destroyed. Some interpretations suggest, though this remains entirely speculative, that the quantum foam might serve as a kind of cosmic memory storage system, preserving information about every event that has ever occurred in ways that we cannot currently access or decode. If true, the space around you right now would contain quantum echoes of every star that has ever formed, every black hole that has ever evaporated, every conscious thought that has ever been generated across billions of years of cosmic evolution. As you rest here, breathing slowly in the quantum-rich environment of ordinary space, take a moment to appreciate the invisible complexity that surrounds every atom in your body. The vacuum between the particles in your cells teems with virtual particles and fluctuating fields that connect you to the deepest structures of reality. You exist not in emptiness, but in a cosmos alive with hidden activity at every level of scale. The dance between visible and invisible matter in our galactic neighborhood creates patterns of motion and structure that have persisted for billions of years, shaping the cosmic environment in ways that extend far beyond the immediate vicinity of individual black holes. This gravitational choreography operates according to mathematical principles that reveal the deep underlying order in apparent cosmic chaos. Consider how the orbital motion of our entire solar system around the galactic center is influenced by the cumulative gravitational effects of all the massive objects in our cosmic region, including the invisible population of stellar mass black holes. Our Sun completes one orbit around the galaxy approximately every 225 million years, following a path that has been subtly shaped by gravitational encounters with countless stellar neighbors, some visible and others forever hidden from direct observation. During each of these galactic years, our solar system experiences what astronomers call galactic seasons, periods when we pass through different regions of the galaxy with varying concentrations of stars, gas, and other massive objects. Some researchers have proposed that these galactic seasons might influence everything from the rate of cosmic ray bombardment reaching Earth to the frequency of cometary impacts on our planet. The black holes scattered throughout our path around the galaxy serve as invisible waypoints in this cosmic journey, their gravitational fields creating subtle perturbations in our solar system's motion that accumulate over millions of years. These effects are far too small to notice on human timescales, but they represent part of the complex gravitational environment that has shaped the evolution of our planetary system across geological time. As you contemplate this vast choreography of cosmic motion, notice how it places your own existence within a framework of unimaginable scale and duration. Every breath you take occurs within a solar system that is dancing through the galaxy in patterns influenced by invisible partners scattered across hundreds of light years of space. You are part of a cosmic ballet that has been unfolding for billions of years and will continue long after every trace of current human civilization has vanished. The mathematical precision required to model these gravitational interactions reveals something beautiful about the underlying order of the universe. Despite the apparent complexity and chaos of galactic dynamics, the motion of stars and stellar systems follows predictable patterns governed by equations that reflect fundamental symmetries in the structure of space-time itself. Recent computer simulations of galactic evolution can now track the motions of millions of individual stars across billions of years, revealing how gravitational interactions gradually reshape the distribution of matter throughout the galaxy. These models show that the invisible population of black holes plays a crucial role in this evolution, serving as gravitational anchors that help maintain the spiral structure of galaxies like our own. So here we are, floating together on a pale blue dot in a galaxy populated with invisible giants, some lurking closer than we ever dared imagine. We've discovered that the cosmic monsters hiding in our neighborhood aren't threats to fear, but reminders of how strange and magnificent our universe truly is. From Gaia BH1 at 1,560 light-years to the possibility of primordial black holes passing through our planet like cosmic ghosts, we've learned that reality extends far beyond what our eyes can see. The darkness between the stars isn't empty but alive with quantum whispers, gravitational waves, and possibilities we've barely begun to explore. Tonight, as you drift towards sleep, carry this knowledge gently. You're part of something infinitely more mysterious and beautiful than we ever imagined, surrounded by invisible wonders that remind us the universe delights in keeping its deepest secrets just beyond our reach. If tonight's neighborhood has stirred exploration of our cosmic red, your curiosity about the deepest mysteries of existence, you might be fascinated by our next journey together. Big Bang Theory is wrong. Roger Penrose drops a bombshell, where we'll examine how one of physics' most brilliant minds is proposing a revolutionary vision of cosmic history that could overturn everything we thought we knew about how the universe began, how it evolved, and what its ultimate fate might be. Until then, sleep peacefully in the knowledge that you're part of a cosmos more magnificent and mysterious than any of us have yet imagined, surrounded by wonders that await discovery in the gentle darkness between the stars.